So the final thing I'll try doing is having a function that calls another function. This is about as complicated as things get. I haven't actually prepared this, so it might be quite entertaining. So where we've got to is we have, oh no, we weren't using that. We are going off on our thing test.s, and this is a very minimal thing we had with maths. So this is a .text section that contains executable code. I'm going to try and do something that calls puts. So if I want to call puts, I need to actually have a string. And the way that we were doing strings is .ascii, and then I can put something in. One of the things I have to be careful about is that the strings that we saw actually included the null terminators themselves. Nothing is expected in assembly. You have to do everything yourself. So if I put in an octal thing at the end, so this is wibble wobble and then a null terminator at the end. This is read-only data, which means it goes in the .read-only data section. No, is it R data? .r data. Yeah, that's right, I think. I also need a label for this thing, so I'm going to call it message. So now I've got a message in an R data section. I've got a text section. Don't know why I formatted it like this. Could do it however I want. So I've got a message in a section, and I don't want this anymore. So what I want to do is call puts, and according to our calling convention, I can find it. The way that we're going to call a function is we will load the arguments into A0 through A3, which is 4 through 7. Got global pointer, stack pointer, frame pointer, return address. We're going to have to be careful about the return address because we have received where we should return to in 31, but we also need to tell puts to return to us in register 31. So one of the things we need to do is, well no, let's do this badly first. So let's call the function and not worry about clobbering register 31. So in order to call the function, I need to load the address itself of the message. So there's this thing called LA, load address. It's not part of the MIPS instruction set. This is a kind of pseudo assembly thing. So this will actually expand into some more primitive instructions that the assembler sort of conspires to actually make work. So if I do load address, I will put it in register 4 because that's the first argument, and the thing that I load will be message. So that's the argument setup. The next thing I need is to load the address into, where do I want to put it? I'll put it into temporary 0. Actually, maybe I should use the A0. So I'll be a bit more disciplined. A0 for the first argument. I'm going to use the first temporary, and the thing I'm going to load into first temporary is the address of the puts function. Notice that puts doesn't appear anywhere here, and that's because puts is going to come from somewhere else. So the linker is going to say this is the address of puts at some point later on. So to actually make a function call, well, a function call is a jump to an address, which we've got here, and we need to link it so we come back to where we will continue. So jump and link T0. This is wrong. I mean, this is not going to work. Not least we've got a jump after a jump. Let's make things mildly happier. So notice that jump and link register is going to overwrite address 31 and make it point to here. Jump to 31 is going to jump back to here. So we immediately have an infinite loop in here. But let's see if it prints wibble wobble. So I'll assemble it. run it, it prints wibble wobble, and then it goes into an infinite loop. We can see that it's in an infinite loop by, if I press Control Z, I can send it to the background. If I do FG, I can bring it back into the no, if I do background, I can send it properly into the background. So it's now running again in the background. If we do top, we can actually see that QEMU MIPS is happily taking up 100% of CPU, bouncing back and forth between those two instructions. If I bring it back into the foreground, it's now running, and I can do Control C to actually kill it. So let's do this properly. Let's actually save the addresses. So we have a stack pointer. Somebody else has told us where our stack is, and it's currently in this register $SP. The stack grows downwards, I believe. We should probably check that. Usually stack grows downwards, which means, see, there are other excellent lecture notes around. I just happened to pick up this. Oh, I don't know. Let's try sending it down, why not? So stack pointer is stack pointer minus 4, because that gives us one word of space. Store words. The thing we want to store is register 31, so let's try that. And we want to store it at the current location of the stack pointer. Once we come out, I'm going to put a bit of space in here. So this part is setting up the stack, so we're storing 31 on the stack. I'm going to leave that NOP in there. Here we need to actually pull the thing out of the stack, so we'll bring it back into 31. We'll bring it off there. And we also need to restore the stack pointer to wherever it was, which is adding back on again. And hopefully this will have saved 31, this will have stored 31, and so we can jump back. I have no idea if this is going to work. So let's try compiling that. Ooh, interesting. I've done it the wrong way around. So it should be $0 SP, I believe, and $0 SP. Okay, so let's try again. Awesome, wibble wobble. And it appears that nothing's gone terribly wrong with our stack, so the whole thing seems to have worked. We can double check that something decent is happening by saying add IU dollar V0, the return value, $0 for 0, oops, there's not dollar, and I don't know, 55, why not? Run it, and 55. Okay, so we're able to call a function in another library. We don't know where the address of that thing is, but who cares, the linker does. And we've actually saved things on the stack and then restored things over, so we can actually manage the stack. This is not brilliant practice because I'm playing a bit fast and loose with the frame pointer. We'll ignore that for now. I'll come back to that in lectures.